what if I told you that nothing is actually, well, one of the most fascinating and complex concepts in the universe? It sounds simple enough, right? Just empty space. But if you've ever really stopped to think about it or, tried to create it, you find out nothing is far from simple. Today, we're taking a deep dive into the concept of vacuum. We've got a fantastic source here, the Wikipedia article on vacuum, and it gives a really comprehensive overview of this mind-bending topic.
Absolutely. And our mission today is basically to unpack what a vacuum truly means. We'll look at everything from its ancient philosophical roots right up to its cutting-edge role in quantum physics. We'll explore how we measure it, how we use it every day, even its kind of surprising effects on living things. You might just find that this empty space is, well, it's pretty much everything but empty.
Okay, let's start at the very beginning then. When we talk about a vacuum, what exactly are we talking about in, simple terms?
Well, at its absolute core, a vacuum is just space devoid of matter, really truly empty. But in practice, it's more of a spectrum. We often think about an ideal or perfect vacuum, sometimes called free space, where there are absolutely zero particles. That's mostly theoretical, though. What we actually create and work with are partial vacuums.
Zero vacuums.
Yeah, regions where the gas pressure is just significantly lower than the air pressure around us, atmospheric pressure.
So it's more about degrees of emptiness then, like how empty can these partial vacuums actually get? Can you give us a sense of that scale?
Yeah, absolutely. The quality of a partial vacuum is basically measured by how much stuff, how much matter is left. Your everyday vacuum cleaner, for instance, it only reduces air pressure by maybe 20%. Not that much, really.
Okay.
But in science and industry, we create something called ultra-high vacuum, UHV, chambers. These are really sophisticated systems. They can reduce pressure to less than 1/trillionth. That's 10 to the minus 12 of atmospheric pressure.
Wow, 1/trillionth.
Yeah. Inside a chamber like that, you might only find about 100 particles per cubic centimeter. It's incredibly sparse.
And that's in a lab environment. What about, out there?
Yeah.
In space?
All right, outer space.
Yeah.
That's our best natural vacuum, and it's even emptier. In the vast stretches between galaxies, intergalactic space, you might find just a handful, maybe a few hydrogen atoms per cubic meter. It's just mind-bogglingly empty.
Incredible.
And just a fun little side note on the word itself. Vacuum comes from the Latin vacuous, meaning empty or void. And it's actually one of the few English words of two used back-to-back.
Huh, never noticed that. Okay, let's dive into this a bit deeper then. How did humans even begin to wrap their minds around this idea of truly empty space, especially when it's so hard to actually make one?
Well, it's a fascinating journey, really. For centuries, the whole idea of a vacuum wasn't just a scientific question. It was a profound philosophical puzzle. Ancient Greek philosophers debated it constantly. You had thinkers like Democritus, part of the atomist school, who argued that a void, an emptiness, had to exist for atoms to move around in. Makes sense, right?
Yeah, logically.
But then you had really influential figures like Plato, who were skeptical, and Aristotle. Aristotle famously championed the concept of horror vacuum.
Horror vacuum.
Yeah, literally, nature abhors a vacuum. He believed any empty space would just instantly be filled. His argument was kind of clever. If a true vacuum existed, motion through it would have zero resistance, right? So things could move infinitely fast or keep going forever. And he just found that idea impossible, illogical.
So for a long, long time, the sort of dominant thinking was, vacuum? Nope. Can't exist. Nature fills the gaps.
Exactly. That view held sway for centuries. Even into medieval times, many scholars, like the Muslim philosopher al-Farabi, flat out rejected the vacuum. Although, interestingly, another scholar, al-Biruni, later pointed out there wasn't actually any observable evidence against it existing. A subtle but important shift. And then there's a really pivotal moment in 1277. The Bishop of Paris, Etienne Tempier, issued these condemnations, basically theological arguments. But in asserting God's absolute power, they implied God could create a vacuum if he wanted to.
Ah, okay. So it cracked the door open, philosophically speaking.
Precisely. It allowed for the possibility of a supernatural void beyond the cosmos, which started to change the intellectual landscape. People could at least consider it.
So the philosophical barrier began to crumble. When did science really step in and say, hey, not only is this possible, we can actually make one?
That really kicks off in the 17th century. It was a huge part of the scientific revolution. In 1643, Evangelista Torricelli, he was working on barometers, studying atmospheric pressure. He accidentally created the first laboratory-sustained partial vacuum. We now call it a Torricellian vacuum. That was massive.
The first actual man-made emptiness?
Well, partial emptiness, yeah. Then, in 1654, Otto von Guericke took it way further. He invented the first proper vacuum pump, and he demonstrated its power with that incredible Magdeburg hemispheres experiment. You've probably heard of it.
The one with the horses.
That's the one. He pumped the air out from between two large metal hemispheres fitted together, and then teams of horses couldn't pull them apart.
Just from the air pressure outside, pushing them together.
Exactly. An incredible demonstration of atmospheric pressure, and by implication, the power of the vacuum inside. After that, you had Robert Boyle and Robert Hooke improving the pump technology. By the 19th century, with things like mercury displacement pumps developed by August Tipler and Heinrich Geissler, scientists could get much better vacuums. And this allowed them to explore new things, like the electrical phenomena in Crookes tubes, the precursors to X-ray tubes and TVs.
Right.
So these experiments really shifted the whole thing from a philosophical debate to something you could actually measure and work with in the lab. It even led to discarding older ideas, like the luminiferous ether, that substance they thought light needed to travel through. Experiments just couldn't find it.
Fascinating. A real journey from impossible to experimentally real. But okay, let's connect this history to the bigger picture now. That historical understanding laid the groundwork, but modern physics. It defines vacuum in really precise and honestly sometimes pretty weird ways, doesn't it?
It really does. Things get much stranger, especially when you get to quantum mechanics. But even in classical physics, the definition is quite strict. Classically, the tightest definition of a vacuum is a region where absolutely everything is zero. No energy, no particles, no momentum, no forces like electromagnetism, nothing. Truly empty in the classical sense.
Okay, devoid of all matter and energy fields. But what about gravity? Can a vacuum still have gravity?
Ah, that's a great question, and it highlights a subtlety. According to Einstein's general relativity, even if you have no matter or energy, what we call a zero-stress energy tensor, space-time itself can still be curved. Think about a black hole that has no electric charge. Outside the event horizon, it's technically a vacuum in terms of particles and fields, but space-time is incredibly warped. You feel strong gravitational effects like tidal forces.
So vacuum doesn't necessarily mean flat, empty space.
Exactly. Gravity can still exist and propagate through it as gravitational waves, for instance. And for electromagnetism, we talk about the vacuum of free space. This is like our perfect baseline medium. In this vacuum, light travels at its absolute maximum speed, that famous C, 299,792,458 meters per second. And crucially, effects just add up. The superposition principle holds perfectly. It has specific properties like permittivity and permeability that define how electric and magnetic fields behave in pure emptiness.
Okay, now here's where I think it gets really interesting. If classical physics basically says a vacuum is empty, what does the quantum world have to say? Because I keep hearing it completely flips the idea of nothing on its head.
It absolutely fundamentally does.
Yeah.
The quantum vacuum is, well, it's mind-bending because it's not empty at all. Far from it.
Yeah.
In quantum physics, a vacuum isn't defined by absence, but as the state with the absolute lowest possible energy, the ground state of whatever quantum field system you're looking at, like QED for electromagnetism or QCD for the strong force.
Lowest energy state.
Okay.
But not zero energy. Not empty.
Not zero, and definitely not empty. The key insight from quantum field theory, and it's backed by experiments, is that empty space is actually this seething, dynamic, fluctuating realm.
Fluctuating? What do you mean by fluctuating? Like, is stuff just appearing?
Sort of, yeah. Think of it like the surface of the ocean. Even on a calm day, there are tiny ripples and waves constantly appearing and disappearing.
Right.
The quantum vacuum is similar. There are these constant vacuum fluctuations where pairs of tiny fleeting virtual particles like an electron and its antiparticle, a positron, spontaneously pop into existence for incredibly short moments.
Pop into existence from nothing.
From the vacuum energy, yeah. They borrow a tiny bit of energy, exist for a fraction of a second allowed by the Heisenberg uncertainty principle, interact, and then annihilate each other, disappearing back into the vacuum.
Wow, okay. And these aren't just like theoretical math.
Oh no, these are real. These vacuum fluctuations have measurable, experimentally verified effects. Things like the spontaneous emission of light from an excited atom it's kicked by these virtual photons, or the Lamb shift, which is a tiny shift in the energy levels of hydrogen atoms caused by interaction with these virtual particles. Even the force between electric charges is slightly modified by this vacuum activity.
So the emptiness is actually mediating forces and affecting particles.
Exactly. There's also this concept of vacuum energy itself, the baseline energy that remains even in the lowest state, and it gets even wilder. Some theories, like string theory, propose a vast landscape of possible quantum vacuum states, each with different fundamental constants and laws of physics. Our universe might just be sitting in one of these many possible low-energy valleys.
Okay, my head hurts a little now. From Aristotle saying no way to space teeming with virtual particles, that's quite a leap. All right, let's bring this back down to Earth, or maybe out to space. From the super theoretical to the practical. Where do we actually find vacuums? How do we measure these different levels of emptiness? And what do we actually do with them?
Right. Well, our best and biggest natural vacuum is, as we said, outer space. It's an incredibly low-density, low-pressure environment. But it's crucial to remember, it's never a perfect vacuum.
Yeah.
Even way out between the galaxies, you've still got those few hydrogen atoms per cubic meter, plus cosmic rays, neutrinos, background radiation.
So not truly empty.
Not truly. And Earth's atmosphere doesn't just stop, it fades out gradually.
Mm.
We often use the Kármán line, about 100 kilometers up, as a sort of conventional boundary for space. The pressure there is incredibly low, something like 32 millipascals. Beyond that, the gas pressure is so low it's almost insignificant compared to things like the radiation pressure from the sun or the solar wind. We start talking about particle density instead of pressure.
And does that very thin atmosphere still matter, say, for satellites?
Oh, absolutely. Even in low Earth orbit, LEO, where the space station and many satellites are, there's still enough atmospheric density, enough particles to cause significant drag over time.
So they have to keep boosting themselves up?
Yep, they need to fire thrusters periodically to maintain their altitude. On the flip side, people are developing concepts like solar sails, which use the tiny push from sunlight radiation pressure for propulsion in that near vacuum.
Clever. And you mentioned background radiation.
Yeah, the whole observable universe is filled with the cosmic microwave background radiation, the afterglow of the Big Bang. It keeps everything at a baseline temperature of about 3 Kelvin, just above absolute zero. So even the emptiest space has this energy field.
Okay, so outer space is a vacuum, but a very specific, not quite perfect kind. How do we actually quantify these different levels of emptiness back here in the lab?
Good question. The quality of a vacuum, as we touched on, is basically about how little matter is left. Lower gas pressure means higher quality. A really key concept here is the mean free path, the MFP.
Mean free path.
Yeah, it's the average distance a gas molecule travels before it bumps into another molecule. Now, in normal air, molecules are constantly colliding. The MFP is tiny, like 70 nanometers.
Yeah.
But as you remove molecules, as you lower the pressure, the MFP gets longer and longer.
Okay.
When the MFP becomes longer than the size of the container you're in, things change fundamentally.
Yeah.
Molecules start hitting the walls of the chamber more often than they hit each other. At this point, standard fluid dynamics doesn't really work anymore. You're in the realm of high vacuum, or UHV, and you have to think about individual particle dynamics.
Ah, I see. So the definition of high vacuum depends on the scale you're working at.
In a way, yes. It depends on the relationship between the MFP and the system dimensions. And we categorize these vacuums into ranges, usually based on pressure. You have low or rough vacuum, medium high vacuum, HV, ultra high vacuum, UHV, and even extreme high vacuum, XHV.
And getting to UHV or XHV sounds difficult.
Extremely. It requires specialized materials like low-carbon stainless steel, all-metal seals instead of rubber gaskets, incredibly thorough cleaning procedures, and often something called a bake-out.
Bake out, like cooking the chamber.
Essentially, yes. You heat the entire vacuum chamber, sometimes for days, to drive out water vapor and other molecules that might be stuck to the surfaces. It helps achieve those incredibly low pressures. And for units, the standard SI unit is the Pascal, Becquerel di Fitino, but you'll often hear torr, which is based on millimeters of mercury in a barometer. One torr is about 133 pascals.
Right. And measuring these pressures must require different tools, too.
Absolutely.
Yeah.
You can't use a regular pressure gauge for high vacuum. For relatively low vacuums, you might use a capacitance manometer that measures diaphragm deflection. For higher vacuums, you use things like thermal conductivity gauges. A Pirani gauge is a common one, which measure how much heat is carried away by the remaining gas molecules. Fewer molecules mean less heat transfer.
Okay.
And for really high and ultra-high vacuums, you need ionization gauges. These basically zap the remaining gas molecules with electrons, turning them into ions. Then they measure the tiny electrical current produced by these ions.
The fewer ions, the better the vacuum.
Exactly. Hot cathode gauges can get down to about 10 aria torr, which is pretty deep into UHV territory.
Okay, so we can define it, we can measure it, but what do we actually do with all this meticulously created emptiness? What are the uses?
Oh, the uses are incredibly diverse. One huge category is simply protection or creating an inert environment. Think of old incandescent light bulbs. The vacuum, or sometimes inert gas fill, stop the hot filament from oxidizing and burning out instantly.
Right, classic example.
It's also crucial for processes like electron beam welding or cold welding, where you don't want atmospheric gases interfering. And of course, vacuum packing food removing oxygen prevents spoilage. And as we mentioned in high-tech manufacturing, like making semiconductors or optical coatings, you need UHV to keep surfaces atomically clean during deposition processes. Any contamination ruins the device.
So keeping things pure. What else?
Removing obstruction is another big one. Particle accelerators need vacuum so the particle beams don't scatter off air molecules. Same for electron microscopes. The electron beam needs a clear path. It's also fantastic for thermal insulation. Your thermos bottle works because the vacuum between the inner and outer walls prevents heat transfer by conduction or convection.
Ah, the thermos. Yeah.
Vacuum also lets you lower boiling points. This is key for freeze drying, where you remove water from food at low temperatures. It's used in preparing certain adhesives, in chemical distillation, and in metallurgy. Then there are the electrical properties. Vacuum tubes, like old radio tubes or cathode ray tubes in older TVs and monitors, relied on electrons moving freely in a vacuum. Modern high-voltage vacuum interrupters also use vacuum to quench electrical arcs.
And just plain suction, right? Mechanical advantage?
Well, technically it's atmospheric pressure doing the work, but yes, we use vacuum to create pressure differences. The very early Newcomen steam engine actually used condensing steam to create a vacuum, which pulled the piston down. There was even an experimental atmospheric railway designed by Brunel that used vacuum.
No way.
Yep. More practically, vacuum brakes were used on trains for a long time. And in cars, the engine intake manifold creates a vacuum that's used to power the brake servo. That's what makes your brake pedal easier to push.
Ah, the brake booster.
Exactly. And in power plants, steam turbines rely on maintaining a strong vacuum in the condenser to maximize efficiency. They use steam jet ejectors or large vacuum pumps to pull that vacuum. It's really everywhere once you start looking.
It really is amazing how many everyday things and cutting-edge technologies rely on carefully controlling, well, nothingness. Now, this does raise an important question. You mentioned how hard it is to get UHV. While vacuum is incredibly useful, creating and maintaining it clearly isn't straightforward. And what about its effects on living things? We see dramatic stuff in movies, but what's the reality?
That's right. Creating a good vacuum is one challenge. Keeping it is another. The biggest enemy is often outgassing.
Outgassing?
Yeah. Basically, all materials have some tendency to release gas molecules, especially when put into a vacuum. Think of plastics releasing volatile compounds or metals slowly releasing trapped gases like hydrogen. Even just water molecules absorbed onto the chamber walls are a huge source.
So the materials of the chamber itself start polluting the vacuum.
Exactly. It acts like a tiny, persistent leak, and it often sets the ultimate limit on how low a pressure you can achieve. Water is usually the biggest culprit in typical high vacuum systems.
And that's why you need the special materials and the bake-out for UHV?
Precisely. You choose materials with very low outgassing rates, like specific stainless steels or ceramics. You ensure everything's incredibly clean. You use metal seals, and the bake-out helps drive off that surface water and other volatile stuff temporarily, allowing the pumps to get ahead. Sometimes they even use cryopumping cooling surfaces with liquid nitrogen to freeze out remaining gases.
Wow. It's a constant battle against escaping molecules. And the pumping itself, how does that work? You said it's not really suction.
Correct. Suction is a bit of a misleading everyday term. You don't really pull a fluid out. What pumps do is create a space with lower pressure, and then the higher pressure outside pushes the fluid into that space. Think about how your diaphragm works when you breathe. It contracts, expands your chest cavity volume, which lowers the pressure in your lungs, and then the higher atmospheric pressure outside pushes air in.
Okay, so it's about expanding volume.
Fundamentally, yes, for many pump types. Positive displacement pumps, like an old-fashioned hand water pump or many industrial vacuum pumps, work by repeatedly sealing off a volume of gas, moving it, exhausting it, and then expanding the cavity again to trap more gas from the chamber. There are other types too, like momentum transfer pumps, turbo pumps that use fast spinning blades to knock gas molecules toward the exhaust, and entrapment pumps, like ion pumps or cryopumps, that trap gas molecules on surfaces.
It sounds like a whole field of engineering in itself.
It absolutely is. It's called vacuum technique. Getting to really low pressures, especially UHV or XHV, requires careful consideration of everything: pump types and stages, seals, chamber geometry, materials, cleaning procedures, leak detection. Even things you wouldn't expect, like how water can slowly permeate through certain metals, or the grain direction in metal flanges affecting sealing.
Good grief. So what are the lowest pressures we can actually achieve?
In the lab, directly measured pressures have reached around 1 by 10 millitorr. Indirect measurements, like in cryogenic experiments near absolute zero, suggest effective pressures down to maybe 5 by 10 millitorr. That's incredibly empty, maybe 100 particles per cubic centimeter. Very close to nothing, but still not absolutely perfect.
Still fighting those last few particles. Okay, so we build these amazing systems to get as close to nothing as possible. But what about us, humans, animals? What actually happens if someone is exposed to that kind of environment? Forget the exploding heads in sci-fi.
Yeah, let's debunk that myth right away. Exposure to vacuum is definitely lethal, but it's not nearly as graphic or instantaneous as movies often portray. The immediate effects would be loss of consciousness within maybe 10-15 seconds due to lack of oxygen, hypoxia. Death would follow within a couple of minutes from that oxygen deprivation.
But no boiling blood.
No, your blood will absolutely not boil. The pressure inside your circulatory system, maintained by the elasticity of your blood vessels, is high enough to keep the boiling point of your body fluids well above normal body temperature, 37 degrees C, even in a vacuum.
Okay, if that's one myth down, what is the real danger then, besides suffocation?
The main physiological effect, besides hypoxia, is something called ableism.
Igbulism.
Yeah, it's the formation of gas bubbles, mostly water vapor in your bodily fluids because of the very low external pressure. This would cause significant swelling. The body might bloat to roughly twice its normal size. Circulation would be severely impaired.
Sounds unpleasant, would you? Rupture.
Surprisingly, no. Human skin and tissues are remarkably elastic and also somewhat porous. While the swelling would be dramatic, you wouldn't actually burst open like an overfilled balloon.
Okay. That's slightly less horrifying. Is it survivable?
Brief exposures can be. There were accidents during high-altitude suit testing and also animal studies. NASA did experiments with chimpanzees in the 60s. The data suggests that if you're repressurized within about 90 seconds, you can make a full recovery, although the experience would be traumatic. Much longer than that, and the combination of hypoxia and circulatory disruption from ebullition becomes fatal.
90 seconds. That's a very short window.
Very short. Minor effects would include the moisture on your skin and in your mouth boiling away rapidly, which causes cooling and frost formation. But that's not the life-threatening part.
What about plants or other organisms?
Plants can actually survive low-pressure environments, down to about 1.5 kPa for around 30 minutes. And some microorganisms, particularly extremophiles like tardigrades, water bears.
Oh yeah, those indestructible little things.
Exactly. They can survive vacuum conditions for days or even weeks by going into a dormant state called cryptobiosis. They are true masters of surviving the void.
Tardigrades win again. Okay, so direct vacuum exposure is bad, causes ableism and hypoxia, but maybe survivable briefly. You mentioned suit testing. What's the real danger in space or high-altitude scenarios?
Often, the far more immediate and dangerous threat isn't the vacuum itself, but rapid decompression, a sudden explosive drop in pressure.
Why is that worse?
Because of the air trapped inside your body, primarily in your lungs. If the external pressure drops instantly, the air in your lungs expands violently. If you happen to be holding your breath, or even if the decompression is just too fast for the air to escape normally through your airways, it can cause fatal rupture of the lung alveoli, the tiny air sacs. This is called pulmonary barotrauma.
So it's like an internal explosion.
A catastrophic overpressure, yes. That's why pilots are trained never to hold their breath during a rapid decompression. Even a relatively small, sudden pressure drop, maybe just 13 kPa or 100 torr, which would be harmless if gradual, can be instantly fatal if it causes lung rupture. You can also get other barotrauma, like ruptured eardrums or sinuses, bruising, internal bleeding. The shock itself accelerates oxygen consumption too. Rapid decompression is incredibly dangerous.
That's a really crucial distinction. The speed of the pressure change is key. It makes you appreciate spacesuits and pressurized cabins a whole lot more. Okay, so wrapping this all up, what does this all mean? We've gone from ancient philosophers absolutely fearing the void to quantum mechanics telling us empty space is buzzing with activity. This deep dive into vacuum, it really feels like it challenges our basic understanding of reality.
It absolutely does. It's really a testament to human curiosity and ingenuity, isn't it? We went from thinking a vacuum was fundamentally impossible, a violation of nature, to not only proving it exists, but developing incredibly sophisticated ways to create it, measure it, and harness it for everything from making light bulbs to manufacturing computer chips, exploring fundamental physics, and even understanding its rather dramatic effects on life. The vacuum isn't just an absence, is it? It's this dynamic stage. It's where fundamental physical processes play out. It constantly forces us to refine what we mean by empty.
Yeah. And when you think about those really mind-bending ideas, like the quantum vacuum fluctuations, these virtual particles just popping into existence from seemingly nowhere, or that theoretical string theory landscape with maybe countless different types of vacuum states, different universes potentially, it really makes you wonder, doesn't it? How much more is our understanding of empty space going to be completely revolutionized in the future? What other nothings are still out there waiting to be discovered that might actually turn out to be, well, everything?